Hello there, this is Brian Buchanan bringing you this tutorial on essential physics in critical care ultrasound. The goal for this tutorial is to provide you with the basic and practical knowledge of ultrasound physics. We want you to provide you with the basic cognitive skill set to understand how ultrasound is generated and how this affects interpretation. We recognize these may be challenging concepts, and we'd encourage you to revisit it at any time. Some of this content may be new to you, and again, may require some review. This presentation heavily references these three articles, which again are source documents if you wish to explore further. Ultrasound refers to sound waves of a frequency greater than the human ear can appreciate. The audible range is 20 to 20,000 Hertz, as you can see there in blue. Frequencies greater than 20,000 Hertz or 20 kilohertz is considered ultrasound. The range of medical ultrasound is usually between 2 MHz and 20 MHz. Sound waves are a longitudinal wave for mechanical vibration. Properties of sound waves include frequency, wavelength, amplitude, and period. Frequency is the number of repetitions or cycles per second, which is measured in hertz. Wavelength is the distance between excitations, or really peak to peak. Frequency and wavelength are inversely related. That is, as frequency goes up, wavelength goes down, and as frequency goes down, wavelength goes up. What are the clinical implications? Well, essentially, short wavelength ultrasound offers the best resolution, but really there is much difficulty penetrating bodily structures, so it doesn't offer a lot of deep tissue visualization. Long wavelength ultrasound can penetrate more deeply, much less resolution, and each ultrasound transducer will have a characteristic frequency. This is kind of akin to basically FM or high frequency radio versus AM or long wavelength radio, where we can see the differences in range and quality of acoustics. Amplitude refers from average to maximum or minimum and is measured in decibels. Amplitude helps define the brightness of the image and is the ultrasound equivalent of loudness. Interestingly, the amount of reflected energy that is picked up by the transducer is only a small fraction of the initial strength of the emitted ultrasound wave, as the wave undergoes a process called attenuation. Other features which we'll not cover extensively include power and intensity. Power is proportional to the amplitude squared, and intensity is power over the beam cross-sectional area. Finally, the speed or propagation velocity at which an acoustic wave travels through the medium depends on two things: density and resistance. Dense media transmit a mechanical wave faster than less dense media. Here we'll cover sound generation. First off, we have an alternating electric current, which is in the head of the probe and affects piezoelectric material or crystal, which is in the head of the probe. The mechanical properties of crystals determine the range of sound wave frequencies that are produced. When this electric charge is applied to this crystal, the material expands and contracts, generating effectively mechanical strain. This leads to mechanical pressure waves in what's called the reverse piezoelectric effect. In order for this signal to return, the crystal switches from a transmission into reception mode. The ultrasound waves interact with the medium and different tissue boundaries and reflect back. This leads to deformation of the crystal and generation of the electrical current, something called the direct piezoelectric effect. The cycling of the crystal between generating pressure waves and receiving them back is repeated several thousands of times per second, creating a real-time image. Object appearance is determined by time for echo to return to the probe, depth, and strength amplitude of returning echo, which is brightness. The vertical position of the echo pixel on the screen is based on the time delay between the emission and return of the ultrasound beam. Velocity is assumed to be constant within soft tissue. Therefore, quickly returning echoes reflect superficial structures, and alternatively, slowly returning echoes reflect deeper structures. The horizontal position of the echo pixel on the screen is based on the receiving piezoelectric crystal's location along the transducer. The resulting horizontal and vertical pattern of the dot's brightness and positioning in the vertical and horizontal dimensions creates B mode, or brightness mode, often called 2D image. Waves that are reflected in full and directly back to the transducer will yield the highest amplitude and hence the greatest signal. The strength of the signal in B mode is determined by the amplitude, and the highest amplitude signals get the brightest dots. Sound waves that undergo much attenuation will be reflected back with lower amplitudes, resulting in lower amplitude or less bright signals. This brings us to our next principle, echogenicity. We mentioned that sound waves that return with high amplitudes will reflect brightly. Seen here is a hyperechoic structure on the left-sided image. When sound waves propagate through a medium without any reflection, the screen pixel will be black and the structure is said to be anechoic, or echo-free. The machine interprets this as a dark chasm where no echo shall return. Finally, waves that lose energy after their interaction with tissue will return low amplitude. This is translated into shades of gray, or hypoechoic. Note that the hypo and hyperechoic are terms that are relational. It really refers to reference to surrounding structures. Based on this echogenicity, we see really the full spectrum, and it really depends on what kind of tissue texture is seen in your image. There you have it. You're already wielding some serious knowledge, and we're only a couple minutes in. Earlier on, I mentioned that sound waves that interact with tissue often undergo attenuation, which means they weaken as they propagate in the medium. The two biggest contributors to attenuation are distance and frequency/wavelength. Right, that's back to the basic principles. The farther a sound wave must travel, the poorer this signal and the greater the attenuation. Also, the higher frequency and shorter the wavelength, the less depth we can see. Interestingly, it is the juxtaposition of tissue types or tissue boundaries that makes imaging possible. At this boundary, sound waves can be reflected on the left, which the sound wave is reflected directly back, much like light off a mirror, the primary interaction that really generates a B-mode image. It can be refracted, like light passing through a prism and resulting in directional change. It can be scattered, sending sound waves off in all directions. Small structures, including those less than 1 wavelength in lateral dimension, will result in scattering of the signal. Unlike a reflected beam, scattering results in the ultrasound beam being radiated in all directions, and there is little return of the signal to the transducer. Finally, absorption. The sound wave is lost and converted to heat. Sound traveling in bone undergoes extensive absorption, as an example. But to highlight, although reflection is one factor in attenuation, is really the core principle that generates image in a B or 2D mode image. When the ultrasound beam hits tissue boundary interface, a certain percentage of the ultrasound is reflected back. However, another percentage is still transmitted. This is the reason why you can generate multiple signals along one scan line. The magnitude of the reflected wave really depends on the tissue acoustic impedance. The reflection is greatest at interfaces with huge differences in impedance, like tissue and air. The tissue-air interface generates an intense reflection as air has a much lower impedance than tissue. As a consequence, ultrasound cannot penetrate air-filled structures, such as bowel or alveoli, but you can identify structures around it. In contrast, ultrasound waves can be propagated through fluid-filled cavities with no reflection and no attenuation. Although we refer to reflection as one method of attenuation, it is often viewed separately as technically it is the primary reason ultrasound works in the first place. We highlighted earlier that materials have a property of acoustic impedance. This is defined by the medium stiffness and density. When there's a large difference in acoustic impedance, like tissue or air, or aerated alveoli, few waves will cross the boundary and most will be reflected and or scattered. In this image, you can see the pleura, the tissue-air boundary, but cannot see below it. The part below the pleura is in fact all artifact. You can see here this also applies to tissue and bone at the tissue-bone interface, where there's a high amount of attenuation from the bony cortex. Both of these phenomena are actually a class of artifacts called acoustic shadowing. This leads to the next concept, is that air is really the enemy. This is why you need ultrasound gel. This effectively acts as a coupler. In fact, in the early days of ultrasound, individuals were placed in a bathtub to help provide a conduit from the ultrasound probe to the patient's body. Next, we'll move on to types of imaging. We've covered 2D and B mode, but there's also M mode imaging. This is one of the first modes discovered in ultrasound imaging, and also color Doppler. First off, we can see here our export screen on the left where we can select these different types of imaging. So again, we've covered 2D or B mode imaging already. This generates pixels based on depth or time of the signal to return, what's often referred to as time of flight. The amplitude of the returning signal also generates the level of brightness. M mode, or motion modulation, or time motion display, permits the examiner to measure size and distances very accurately. This provides high temporal resolution with a frame rate that vastly exceeds B or 2D mode imaging, and allows you to see very fine movements, including pleural motion or cardiac valvular motion. We have M mode here of a lung with the time in the x-axis and the imaging plane in the y-axis. This helps us see a seashore sign where the pleura is constantly moving. This is really one scan plane repeated over time. This can also be used to interrogate LV wall thickness as long as you are perpendicular to the LV wall, and can be looked for early diastolic collapse of the right ventricle and tamponade. Next, we have one of the more challenging modes to understand, and that is color Doppler. Don't be frustrated by this. It uses very basic assumptions to recognize flow and direction, things that you probably already know about. Trains help to communicate what this Doppler shifting really is. And we hate to bring you back to grade school, but you may recall the Doppler effect. This is when the source of the sound, the transducer, and the object reflecting the sound, the reflector, are moving in relation to each other. If the reflector is moving towards the source, then sound has become compressed to high frequency. This is registered as a positive Doppler shift. If moving away from the sound source, sound is reflected with lower frequency, which is a negative Doppler shift. In our case, the computer looks for frequency shifts in the blood flow emitted between transmitted and received frequencies. This results in a color map. Here we can see the machine can pick up color flow patterns and even velocities. The color scale or color legend at the top left shows that blood flow towards the probe as red and blood flow away as blue. In fact, the machine even describes basic velocity measurements assigned to selected colors, varying intensities of red and blue. This view is an apical four-chamber. We can see blood flow coming into the RV as red. That's towards the probe and diastole. And a bit of a leak in systole, which is really some mild tricuspid regurgitation, which is blue or away from the probe. BART is the basic acronym. Blue away, red towards. And this really depends on the position of your color scale, as we can see on the top left. The most obvious example of the BART principle is with a phased array probe placed at the supraclavicular notch looking inferiorly. This is at the top portion of the sternum. We can see as blood flows towards the probe, it's red, and as blood flows away, it's blue. This is much like the ambulance that comes towards you and whizzes away. Now, an interesting thing happens if you exceed the velocities in either direction. You get a phenomenon called aliasing. The maximum velocity on either side of the scale is referred to as the Nyquist limit. The maximum velocity the scale can work between. This means that once the velocity of blood flow in one direction exceeds the brightest red, the color will instantaneously change to the brightest blue, then gradually darken. In this apical four-chamber, we can see that normal diastolic flow is red towards the probe. We can look closely and see that in systole, a blue regurgitant jet. That's tricuspid regurg. You can see in the center of the jet some color mixing, a mosaic pattern. This is because the jet exceeds the max regurgitant velocity in the color scale. The machine no longer can interpret the direction or velocity, and you see color mixing. This is much like looking at the propeller on a prop plane. At a certain frequency, we can no longer recognize the direction the prop is spinning in. In this case, the machine can no longer interpret the direction and velocity. This can help pick up areas of flow acceleration, like those of stenosis and regurgitation, where blood is pushed through a pinhole. So we've covered an array of topics from physics of sound wave generation to echogenicity to color Doppler. We know these topics can be quite challenging, and we encourage you to read this tutorial as needed. I'd like to thank you for tuning in and look forward to working with you more.